1 minute ago, somewhere in the driest desert on Earth, a machine the size of a small house opened its eye and looked into the sky, and what it sent back has left astronomers staring at their screens in stunned silence. Because this isn't a simple update. This isn't another routine data release. This is the Vera Rubin Observatory capturing something so vast, so violent, and so unexpected that scientists are now calling it one of the most unsettling nights in the history of modern astronomy. A sky that should have been calm, mapped, familiar, has suddenly revealed a level of chaos hiding above our heads that no one, not even the engineers who built this telescope, was fully prepared to witness. And the strangest part is, this is only the beginning. Because if the first images are already this disturbing, what happens when the machine turns its full power toward the rest of the universe? Tonight, we break down exactly what the Rubin Observatory just captured, why it has triggered alarm inside observatories around the world, and why some scientists are quietly admitting that the sky we thought we knew may not be the sky that actually exists. To understand why this moment feels so seismic, you have to understand what this telescope actually is. Perched atop Cerro Pachon in the Chilean Andes, inside one of the most isolated and atmospherically stable regions on the planet, the Vera Sea. Rubin Observatory was never built to take pretty pictures for their own sake. It was built to watch the sky the way a security system watches a city, constantly, relentlessly, scanning every corner of the visible heavens every few nights without pause. Its heart is the Simony Survey Telescope, an unusual three-mirror design that trades the narrow tunnel vision of most telescopes for something closer to a wide, sweeping searchlight. Attached to it is the largest digital camera ever constructed for astronomy, a machine weighing close to 3 tons, built with 189 individual sensors, fused together into a single 2 billion pixel eye. In practical terms, this camera can capture a patch of sky equivalent to 40 full moons in a single exposure, an area so large that Hubble would need thousands of individual images stitched together just to match it. And this is exactly why what it captured in its earliest test runs has become so disturbing, because a machine built to see everything at once has now shown us just how much has been quietly happening above us the entire time, unseen, unrecorded, and unaccounted for. When the first true test images began arriving from Rubin, astronomers expected something impressive. What they got instead was something closer to shock. In just over 10 hours of observation, the telescope produced a sweeping portrait of the southern Virgo cluster, an image so dense with galaxies, star clusters, and faint smudges of ancient light that scientists nicknamed it the cosmic treasure chest. But treasure was not the word running through everyone's mind. Buried inside that single mosaic were spiral galaxies caught mid-collision, their arms twisted and stretched by gravitational violence playing out over millions of years, frozen in this one frame like a crime scene photograph of the universe. Thread-like filaments connected distant galaxy clusters across unimaginable gulfs of space, hinting at a hidden scaffolding of matter holding the cosmos together in ways we still don't fully understand. And in the background, almost invisible, unless you zoomed deep into the frame, sat a faint reddish haze of countless background galaxies, each one a separate island of billions of stars, sitting quietly in the dark, undiscovered until now. And this staggering image, as overwhelming as it already was, represented only a fraction of 1% of what Rubin is expected to eventually reveal. That number alone is what began putting scientists on edge. Rubin's ultimate goal is to catalog roughly 20 billion galaxies over the course of its mission, an amount so large it's almost impossible for the human mind to hold. But it isn't simply the scale that has unsettled researchers. It's the speed and the violence with which new discoveries are already surfacing. In that same 10-hour test window, the observatory identified more than 2,000 previously unknown asteroids, including several classified as near-Earth objects, meaning space rocks whose orbits bring them uncomfortably close to our own planet. To put that into context, the entire combined network of the world's observatories typically discovers around 20,000 asteroids in an entire year. Rubin matched a meaningful fraction of that in less than half a day of test observation. And this wasn't even Rubin operating at full capacity. This was a trial run, a soft opening, a machine still calibrating itself. If this is what shows up during a test, the real question haunting astronomers now is what exactly is waiting to be discovered once Rubin begins its full 10-year survey of the sky. The unease deepens further when you look at what Rubin captured around the Lagoon Nebula, a massive star-forming region roughly 5,000 to 100 light-years from Earth. Under a normal telescope, this nebula is usually presented as an isolated, almost peaceful-looking cloud of glowing gas, an image cropped tightly enough to feel calm and contained. But Rubin's wide field mosaic shattered that illusion completely. In its version of the same region, the nebula, despite spanning 55 light-years from end to end, occupies only a small portion of the frame. Surrounding it is a crowded, restless neighborhood of open star clusters, a glowing companion nebula, and a tightly packed globular cluster containing stars far older than our own sun, all sitting shoulder to shoulder in a single image. What Rubin revealed is that the calm, isolated pocket of space we thought we understood is actually a densely populated intersection of birth, death, and ancient survivors, layered on top of each other at wildly different distances, hiding in plain sight the entire time behind the narrow field of view of every telescope that came before it. And this is where the deeper anxiety begins to creep in among researchers. Because Rubin isn't simply photographing the sky, it's exposing how much of the sky has been invisible to us until now, not because it was too far away, but because nothing before had ever been wide enough, fast enough, or sensitive enough to catch it. Every 3 nights, Rubin completes a full scan of the visible southern sky, meaning it doesn't just take a picture, it builds a live, constantly updating record of change across the entire heavens. A star that flares unexpectedly gets caught almost the moment it happens. A distant explosion, a stellar collision, a sudden brightening no one predicted, all of it gets logged automatically, without waiting for a human astronomer to happen to be looking in the right direction at the right time. In essence, Rubin has turned the sky from something we occasionally check into something that is now under constant surveillance. And the unsettling truth researchers are beginning to confront is that a sky under constant surveillance behaves very differently from the sky we thought we knew from occasional glances. This shift becomes even more concerning when you consider Rubin's core scientific missions, because tracking asteroids is only one piece of a much larger and more disturbing puzzle. The observatory was also designed to hunt for signs of dark matter and dark energy, the invisible forces that appear to govern the expansion and structure of the entire universe, yet remain almost completely unexplained by modern physics. By mapping how billions of galaxies cluster, warp, and drift across cosmic time, Rubin is expected to produce the most detailed gravitational map of the universe ever assembled. But every additional galaxy it catalogs, every filament of dark matter it traces, adds more weight to a growing suspicion inside the scientific community that our current models of the cosmos may be dangerously incomplete. It's one thing to suspect that we don't fully understand 95% of the universe. It's another thing entirely to have a machine actively proving, image by image, exactly how much of that invisible architecture has been sitting undetected above us this entire time. At the same time, Rubin is quietly building what may become the most alarming planetary defense tool humanity has ever had, and not everyone is comfortable admitting how urgently that tool might be needed. Near-Earth asteroids, the ones capable of causing real damage if their orbits ever intersect with our planet, have historically been difficult to track precisely because most telescopes are too narrow and too slow to catch them before they've already passed by. Rubin's combination of a massive field of view and a rapid 3-day scanning cycle changes that equation entirely. In its earliest hours of operation, it already flagged multiple near-Earth objects that had never been cataloged before, objects that had been quietly crossing space near our planet without anyone on Earth ever knowing they existed. Scientists have long assumed that the vast majority of dangerous asteroids capable of city-level destruction remain undiscovered, hiding in the glare of the sun or slipping past our limited observation windows. Rubin is now expected to find the overwhelming majority of them within just the first few years of full operation, which raises an uncomfortable question few want to say out loud in public. What happens the moment this telescope finds something that's already on a collision course, and how much warning will humanity actually have when that moment comes? Adding another layer of unease is what Rubin's design means for the detection of interstellar objects, the rare visitors that occasionally drift into our solar system from other star systems entirely. Historically, humanity has only confirmed a small handful of these objects, discovered almost by accident, spotted only when they were already halfway through their brief pass by the sun, giving scientists mere days or weeks to study them before they vanished back into deep space forever. Rubin's rapid, wide field scanning is expected to catch these visitors far earlier in their approach, and while there is still time to point other instruments toward them and actually study what they're made of. But this capability comes with its own unsettling undertone, because it means that for the first time, humanity may soon have enough data to seriously investigate the strange, unresolved questions that lingered around earlier interstellar visitors, questions about unexpected accelerations, unusual shapes, and behavior that didn't fully match anything we'd previously classified as an ordinary comet or asteroid. Whether Rubin ultimately confirms mundane explanations or opens the door to something far stranger, one thing is now certain: we are no longer blind to these objects the way we once were, and that alone is already changing the conversation happening quietly inside research institutions. Behind all of these discoveries lies an infrastructure challenge so massive it borders on unbelievable. Rubin is expected to generate roughly 20 terabytes of raw data every single night it operates, an amount so large that traditional data pipelines would simply collapse under the weight of it. To handle this, engineers built a dedicated high-speed fiber connection capable of streaming the observatory's nightly output from the mountains of Chile directly to processing centers in the United States within seconds of capture. From there, an automated system has to calibrate every image, correct for atmospheric distortion, align overlapping exposures, and flag anything that has moved or changed since the last scan, all before a single human scientist has even had the chance to look at the results. Over the full span of its mission, Rubin is projected to accumulate roughly 500 petabytes of astronomical data, an archive so enormous that researchers openly admit it will take years, possibly decades, just to fully comb through everything the telescope has already recorded. In other words, the unsettling discoveries making headlines right now may only be the smallest, earliest fraction of what's actually sitting inside Rubin's growing digital vault, waiting to be noticed. What makes all of this even harder to process is the sheer contrast between Rubin and the space telescopes we've relied on for decades. Hubble, for all its legendary detail, only captures a sliver of sky in each image, an area equivalent to roughly 1% of the full moon, meaning it has always been a tool for zooming tightly into individual objects rather than surveying the broader landscape around them. Rubin flips that entire approach upside down. Instead of a microscope aimed at single points of interest, Rubin behaves like a low-flying drone sweeping across the entire cosmic terrain at once, revealing not just individual galaxies or nebulae, but the sprawling relationships between them, the filaments, the clusters, the quiet neighborhoods of space that have always existed just outside the narrow frame of every telescope that came before it. And once you see the universe this way, wide, connected, and constantly shifting, it becomes almost impossible to go back to thinking of the night sky as something calm, static, and fully mapped. Perhaps the most quietly disturbing element of all of this is how deliberately Rubin was engineered to defy the very reason space telescopes were invented in the first place. Ground-based observatories have always struggled against Earth's atmosphere, the shifting layers of air, heat, and moisture that blur and distort incoming starlight, which is exactly why observatories like Hubble and James Webb were launched beyond the atmosphere entirely. Yet Rubin, sitting firmly on the ground atop Cerro Pachon in the Atacama region, one of the driest and most atmospherically stable places on the planet, has produced images sharp enough to rival, and in specific ways even challenge, telescopes orbiting far above our heads. That alone should be reassuring, a triumph of engineering, but instead, it has left some scientists quietly unsettled by a different implication. If a ground-based telescope can now see this deeply and this widely into the universe, how much has simply been missed over the past several decades of astronomy, hidden not because it was too far away, but because nothing on Earth had ever been built wide enough or sharp enough to catch it until now. And this is precisely why Rubin's true mission feels less like a celebration and more like a warning shot fired quietly into the scientific community. The observatory is preparing to catalog ancient RR Lyrae stars scattered across the furthest edges of the Milky Way, pulsating stellar beacons whose predictable brightness allows astronomers to measure distance with remarkable precision. Already, in its earliest test observations, Rubin identified dozens of these stars, with expectations that the full survey will eventually reveal upwards of 100,000 of them stretching into the galaxy's outer halo. Mapping these distant stars will essentially reconstruct the skeletal structure of our own galaxy, revealing faint tidal streams left behind by long-forgotten galactic collisions, hidden dwarf galaxies that have gone completely undetected, and evidence of violent mergers written quietly into the outer edges of the Milky Way. For decades, this information remained just out of reach, the stars too faint and too scattered to track consistently. Rubin is now poised to turn what was once considered an impossible mapping project into a matter of routine observation, and in doing so, it may reveal that the galaxy we call home has a far more chaotic and violent history than anything currently written into our textbooks. Even the way ordinary people are being invited to interact with this data carries its own strange undertone. Rubin's imagery is being made available through public viewing platforms designed to let anyone, not just professional astronomers, explore its mosaics directly, zooming from sprawling cosmic landscapes down into individual galaxies and clusters with nothing more than a web browser. On the surface, this feels like a celebration of open science, a democratization of discovery that puts unprecedented cosmic detail into the hands of ordinary viewers. But it also means that some of the earliest sightings of new transient events, unexpected flares, unidentified moving objects, faint anomalies buried deep inside these enormous images, may end up being spotted first, not by trained researchers working through structured analysis, but by anonymous members of the public scrolling casually through the data late at night. In an age where the volume of information being generated has already outpaced the number of professional astronomers available to review it, This democratization is less a convenience and more an admission that no institution, no matter how well funded, can fully keep up with what Rubin is producing. There's also a quieter, more human dimension to all of this that rarely makes it into the headlines, and it has to do with just how many people were involved in getting Rubin to this point. The observatory took more than 2 decades from initial concept to first light, passing through generations of engineers, physicists, and software architects who spent entire careers building. Toward a single moment they weren't even guaranteed to see finished. Entire teams dedicated themselves to grinding and polishing that record-breaking primary mirror to a precision measured in millionths of an inch, while separate teams spent years writing the software pipelines that would eventually have mere seconds to process each image before the next one arrived. And now that the telescope has finally opened its eye, all of that accumulated effort has collapsed into a single overwhelming realization that the universe those engineers built a machine to observe turned out to be busier, stranger, and more restless than even they expected. It's one thing to design a telescope to detect activity in the sky. It's another thing entirely to watch it succeed this quickly, this thoroughly, on what was supposed to be nothing more than an early test run. That success has also forced a quiet reckoning inside funding committees and research institutions who now have to grapple with a strange new problem, not a shortage of discoveries, but an overwhelming surplus of them. Traditional astronomy has always operated on a model where a telescope produces a manageable stream of data that a research team can study carefully over months or years. Rubin inverts that model entirely, producing more confirmed discoveries in a single night than many observatories generate in a year, which means the existing infrastructure of peer review, verification, and follow-up observation is already straining to keep pace. Some astronomers have quietly acknowledged that entire categories of transient events, brief flares, sudden brightenings, faint anomalies lasting only a few hours, may simply pass through Rubin's data stream unexamined by human eyes, filed away in an archive too vast for anyone to fully explore in real time. In effect, Rubin isn't just revealing how much has been hiding in the sky, it's revealing how unprepared our scientific institutions are for a universe that finally refuses to hold still long enough to be studied the old-fashioned way. There is also the matter of what Rubin might eventually confirm or deny about phenomena that have lingered on the fringes of serious astronomy for years, treated as curiosities rather than priorities, simply because no instrument existed with the reach to investigate them properly. Unexplained brightness variations in certain stars, faint anomalies in outer solar system objects, unusual clustering patterns that don't fit neatly into existing models of galaxy formation, all of these have persisted for decades, without resolution, largely because the data required to settle them never existed in sufficient quantity or quality. Rubin's constant wide-field monitoring changes that calculus entirely. For the first time, there will be enough repeated observations across enough of the sky over a long enough period of time to either quietly resolve these lingering mysteries, or just as easily, to deepen them into something far more difficult to explain away. And that uncertainty, more than any single image released so far, may be the real reason astronomers are approaching this new era with a mixture of excitement and genuine unease. All of this brings us back to the unsettling core of why this moment matters so much. For as long as modern astronomy has existed, our picture of the universe has been built from narrow windows, isolated snapshots, careful zoomed-in studies of individual objects examined one at a time, with long stretches of darkness and uncertainty in between each observation. Rubin has just shattered that entire framework in the span of a single test run. What it has shown, in its very first images, is that the sky is not the quiet, orderly dome we assumed it to be. It is dense, chaotic, and in constant motion, filled with far more activity, far more hidden objects, and far more unresolved structure than anyone anticipated seeing this early in the mission. A single scan revealed thousands of previously unknown asteroids. A single mosaic captured galaxies locked in the middle of violent collisions. A single wide-field image exposed an entire hidden neighborhood surrounding a nebula we thought we already understood. And every one of these revelations arrived not from years of patient searching, but from roughly 10 hours of test observations, a mere flicker of what this machine is now capable of producing every single night for the next decade. The uncomfortable truth settling over the scientific community right now is simple. If this is what a brief calibration run revealed, then the sky above us has been hiding far more than anyone was prepared to admit, and Rubin has only just begun to look. Every 3 nights from here forward, it will scan the heavens again and again and again, building an ever-growing, living record of a universe that refuses to stay still. Somewhere in that endless stream of incoming data sits the next asteroid on a trajectory too close for comfort, the next galaxy caught mid-collision, the next flicker of light from an event we don't yet have a name for. And as Rubin continues turning its enormous eye toward the darkness night after night, the real question quietly circulating through observatories around the world is no longer whether something unexpected will show up in the data. It's simply a matter of when and just how unprepared we'll be the moment it does.